Okay. Good afternoon, ladies and gentlemen. Good to see you again. This is our last week. As you know, next week is Khmer New Year, and you're going to have one more quiz from chapter 6, okay, next Monday. And again, I will ask similar questions in your final exam. So it's a kind of preparation for your final. Okay. So, and again, that will be around, I think, only 10 questions. All right. So Monday, you will have quiz from chapter 6, okay? And today, I will finish chapter 6. Only one thing is left from here. And we are going to cover the last, actually, section 6.5, work and fluid force. Now, also, we need to cover chapter 7. Chapter 7, actually, it's not a big chapter. It's all about calculation. And the only new thing is we are going to see what is it, transcendental functions. Those are logarithmic functions and also inverse trigonometric functions. Okay, it's just about calculation. The idea, everything it is, there's not much new there. The only thing is we are just going to introduce those new functions and you are familiar with those functions, so it does not take much time. So Thursday and Friday, in 2 days, I think I'm going to cover chapter 7. If time is not enough, maybe I will make 1 or 2 more videos about chapter 7, but we are going to cover 7 chapters, as I told you, as the beginning of the chapter. And how about 6.6? Maybe I will ask your assistant teachers, okay? They will show you a few examples about moments and center of mass. And also, I just want you to see how integral is used there, okay? With engineering students, we will talk about moments and center of mass more, again, later in calculus 3, okay? So that's why now we are running out of time. I'm just going to skip this for now. So now in this video, in this class today, we are going to talk about work and fluid force in this session. And next session, I'm going to start chapter 7. Okay, maybe actually, as you see here, 6.5 and 6.6. These are actually applications of definite integrals. Okay, understanding the problem, you need to model this and blah blah blah. It takes time. Okay, so that's why maybe we may have another problem solving session and solve actually more problems related to these concepts. So guys, now so far we talk about volumes. I mean, we studied volumes, right? How to find volumes using cross sections and volumes using cylindrical shells. These are all applications of definite integral. Some applications, of course, and arc length, right? How to find the length of, let's say, the graph of the function over an integral, and areas of surface of revolution. That is our last topic we studied last Friday. So today we will talk about work and fluid force. What we have here, we have work done by a constant force, work done by a variable force along a line, Hooke's law for springs F equals kx, pumping liquids from containers, and fluid pressures and the forces. Okay, so we are going to talk about this. So of course, one session is not enough. Maybe I will make 2 sessions. Today we will finish anyway. So tomorrow we will actually, Thursday and Friday, we will talk about chapter 7. Okay, now let's start with the first part, actually, work done by a constant force. We know that in our everyday life, right, usually to do something, maybe to carry a chair, even to walk or to play tennis or to kick the ball, you need to exert some force, right? So, for example, very simple definition of a force in physics, okay? not physics, not in daily life. Of course, they are similar things, but sometimes in theory, okay, for example, if you're just walking around and just come back to the same point, maybe you are carrying something, okay, and what is the work done by you? It is zero. So how do we define work in, what is it, physics, right? If you have a kind of ice cube, for example, right, and if you're just pushing this with some kind of, applying some kind of force, horizontal force, all right, and you're just moving this from this point into this point, okay, so the distance between these 2 points, let's say it is d, right? So now what is the work done actually to push this cube from point A, let's say, to point B, right? And this is defined, actually the work done is defined here, the F, right, the magnitude F times D. Okay, so distance, right, you are using this F, right, you're just pushing for a what is it, a distance of D units. That is the definition of work. And we know that the unit of F, it is Newton, and here D, it is meter. So Newton times meter is defined as joule. So that actually we use joule to measure the work done by some kind of force. Okay, but here, of course, that's just a simple formula. Maybe you must have studied in physics. Okay, but here we are going to see how is it related to, I mean, how we can use definite integral, or how come that actually we need definite integral to solve problems related to a force. But usually, okay, if it is constant, as you see here, we don't have to involve any integral here. But how about if at every point, for example, let's say you are pushing, okay, but you're not applying the same force. At every point, okay, the force is used to push this, let's say, the kind of ice cube. It is changing. It's not constant. And simple, let's say F is a function of X. At every point, the force is different, let's say. So at the time, how do we actually find the total work done to push this, again, this ice cube from this point to this point, right? Now, again, here we are just going to use the simple, I mean, the idea of definite integral, because everywhere it is different, right? The force is not constant. So we are just going to divide, let's say this one is from A to B, and we are going to divide this into n sub intervals. If you just take two intervals, let's say this point is x sub k minus 1, and this point is x sub k, right? And what is the work done to move object from x point x sub k minus 1 to x sub k, all right? Actually, if this distance is so small, right? So the approximately, actually, if you just pick any point here, when you're just moving this from this point to this point, our force does not change much, because here we are assuming that our force is a continuous function. And the continuous function means that a small change in the amount of x, right? If you just change a little bit the value of x, and also it produces the small change in the value of the function. Okay, so that means that here, if I just pick any point here, so if I can approximate that work done here, let me say, let me just denote this by WK, work done to push this ice actually cube from point x sub k minus 1 to x sub k, right, is approximately, I'm just saying approximately, is equal to, I'm just picking any point, all right, maybe force here it is different, here different, here different, I'm just approximating. So that's equal to x f of c sub k times the distance, right? Actually, we move this from x sub k minus 1 to x sub k. That's equal to x sub k minus x sub k1, which is equal to delta x sub k. Okay, so now how about the total work actually here done to move this ice cube from A to B? At the time, we should just summing up these works, right? So the total work done here is approximately is equal to W1 plus W2 plus dot dot plus WN. In sigma notation is sigma here. K is equal to 1 to N, right? And WK, that's equal to F of C sub K times delta X sub K. Now here we expect that actually as we just increase the number of subintervals, right? That means that our force, right? When we are moving from x sub k minus 1 to x sub k, it does not change much. And how about if it goes to infinity? What you see here is actually the total work done that gives us that limit, right, as n goes to positive infinity. That means that now we are dividing our subintervals into very, very, very small subintervals. That means if you just moving or covering a short distance, right, during this time, the force almost it does not change. It's like speed time problems, right? So here the sigma k is equal to 1 to n. Here we have f of c sub k times delta x sub k. So actually that's equal to this exactly, because if n goes to infinity, right, that means that actually this x is going through every point, and the interval between two points is almost zero. And what you see here is exactly our Riemann sum, right? Here we have some kind of continuous function, and here we have delta x sub k. So that limit, if it exists, we define this as, what is it? A definite integral from a to b. And here we have f. Since sub k is taking every value of x, that's why here we have f of x, and here we have dx. Okay, so that is how we calculate work done by a variable force, maybe let's say to move an object from point A to point B. And this is how actually integral appears. That's why we're just summing up and infinitely many small things here. And we are just expressing this in very, very simple notation, that is integral notation. Okay. Hooke's law for spring. Okay. As you know, that Hooke's actually one physicist, all right, and his law is famous. One of the, actually, we have a lot of formulas in physics. Anyway, it says that the force required to hold a stretched or compressed spring, x units from its natural or unstressed length, is proportional to x. And what does proportional? It means that if you want to stretch, we are talking about the spring, right? Here we have a spring, let's say, and here the length of the spring is, it is L. Okay, so now if you want to stretch, for example, x units, right? This one is x units, and to do this one, right, we need to actually apply some force. We need to pull this, or either we need to push this, right? And here it is saying that to just pull this, or let's say stretch this x units from its natural length, right? And we need to apply some force. It's saying that that force is in directly proportional to, what is it? The distance stretched by the spring. And directly proportional, that means that actually this force and this x, they increase or decrease at the same rate. Okay, if you want to actually, for example, stretch more, you need to apply more force, right? If you want to, for example, let's say, what is it, compress this more, you need to use more force. So the formula is, what is it? F equals K times X. All right, find the work required to compress a spring from its natural length of 0.3 meters to a length of 0.2 meters if the force constant is K equals 234 Newton per meter. Okay, so here we are talking about a spring. Let's say, let me just draw this vertically to save space. Okay, that is the natural length of the spring. What is it? It is 0.3 meters. Right now, maybe I'm just pushing, or maybe actually this one is maybe ground. Okay, I'm just pushing from the top. All right, I'm just compressing this. It says that find the work required to compress the spring from its natural length of 0.3 meters to a length of 0.2 meters. So now, again, it's the ground, right? I'm just doing this. I am going to compress this. So that now the length, right? This length becomes, what is it? 0.2 meters. So actually, what is x here? It was 0.3, right? How much did it compress this? So our x here is 0.1 meter. Okay. So now from here, we know that it says, okay, find the work. We are going to find work here, right? So 0.1. So if I just actually draw that 0.1 line segment is changing from 0 to 1. That's our x, right? So because we know that if, as you compress this more and more, it requires more force, right? It gets harder and harder. That means that at every point, right, you are applying different amount of force. So that means that x is changing from 0 to 1, right? And also actually f is different at every point. So simply here, what is our f? We know that f is equal to k times x, and the constant of this, or this spring, is given here. That's equal to 234, and that's x. So for example, let's say if x is equal to 0.1, at the time we need 23.4 newtons to keep this at this length, right? For example, if it is, let's say 0.05 something, at that time just put substitute here, we can find what force is applied at this point. Anyway, so now the question is, we need to find the work done, right, to do this thing, to compress this spring. So then work is down here is, what is it? Our x is changing from 0 to 0.1. And here we have f of x, right? This f of x and the dx. And what is our f of x? That is 234x. So here we have 0 to 0, 1, and 234 x dx, which is equal to 234. That's equal to 117 x squared from 0 to 0 0.1, or that's equal to 117. When it is 0, that's equal to 0. When it is 0 0.1, that's equal to 1 over 100. So that's equal to 1.17 joule. Okay, so this much work is done to compress the spring from 0.3 meters to 0.2 meters. Another example, a spring has a natural length of 1 meter. A force of 24 newtons holds the spring stretched to a total length of 1.8 meters. Find the force constant K. Okay, first, okay, we are talking about A. Let me just divide this. So it says that here we are talking about a spring. Okay. All right, that is 1 meter. Just right here, that's 1 meter, right? And after it says that a force of 24 newtons holds the spring stretched to a total length of 1.8. So now, after we stretch this, it becomes, what is it? 1.8. So now, what force is applied here? Here, the force used to keep this at this length, right? It is 24 newtons. Now, from here, using that Hooke's law, that F should be equal to K times X, right? And from here, what force is used to keep this at this length? That K is equal to, our F is 24 newtons and X is 0.8 meters, which is equal to, divide by 8, it is 3, and that's equal to 30. What is it? K, it is Newton, right? Newton meter. So that's it, because this one is meter, right? This one is Newton, so that is Newton per meter. So that is the constant of the spring. What is it? Force spring constant. All right, guys, let's continue. So that's our spring constant, right? And since we know that now, we know how F, K, and X are related to each other. Question B says that how much work will it take to stretch the spring 2 meters beyond its natural length? So that means that if our X is 2, right, that means of here, our X, to change this from 0 to 2, the X is changing, right? How much work is done, or how much work will it take to stretch the spring 2 meters beyond its natural length? And we know that actual work done, right, that's equal to integral, right? So here the force at every point is different, but it's continuous function. X is changing from 0 to 2, and here we have f of x dx, right? So that's equal to integral from 0 to 2. What is f? F is, we know the spring constant, that is 30. So here we have 30x, and here we have dx. which is equal to 15x squared from 0 to 2, right? When it is force, that's equal to 60 joule. So actually 60 joule is of work is done to stretch this for 2 meters beyond its natural length. Okay, question C. How far will a 45 Newton force stretch the spring? Right. So we know the constant again. We are just asking this F is equal to K times X, right? They are related by this equation. It says that how far will a 45 Newton stretch the spring? And spring constant, it does not change. That's why it's constant here. And from here, what is X? So X, how far, right, is equal to F over K. So our force is 45 Newton and K is equal to 30. That's equal to 1.5 meters. That means that if you just apply a force of 45 Newton to this spring, right, it will be stretched for 1.5 meters beyond this natural length. All right. Another problem, a 22 Newton bucket is lifted from the ground into the air by pulling in 6 meters of rope at a constant speed. The rope weighs 1.17 Newton per meter. How much work was spent lifting the bucket and the rope? Actually, maybe if you just add, if you have ever done any kind of construction, right? If you're just pulling that up, as we pull more and more, it gets easier and easier. Why? Because the length of rope is shortening, right? And also rope has some weight, actually just pulls you down, especially if you're using big rope, for example. It can, at the time you can see the difference there. Okay, so the bucket has constant weight, so the work done lifting it alone is weight times distance, right? So here we are talking about the bucket, right? So let me just write here. Number one is we have a bucket here, and okay, and here we have a rope here, and also here we have a rope here, right? Two things. And number one, let's say to actually carry this bucket up to the top of the wall, let's say we need this much work, right? This much work should be done to do this one. And also to pull the whole rope up to the, what is the top of the wall, let's say also we need this much work to be done. So at the time, our total work done will be equal to W1 plus W2, right? So actually this bucket, right, it has a constant weight because as you just move it up, it's not changing, right? And it says that, what is it? It is 22 Newton bucket, right? So what is the work done here? It's just distance times force. So our force, that's at F1 times X1. And how about this one? This rope is changing, right? As you just pull this up, right, actually the length of the rope is changing. And also it says that the rope weighs 1.17 Newton per minute. So at the time, at every point, our force is different. That's why we are going to use different integral here. So the second part is integral, right? So our x is changing from 0 to 6, from 0 to 6, right? And its weight, it is 1.17, what is it? 1.17, what is it? Newton per meter. So here we have 1.17 times, right? So here the distance is 6 minus x. And here we have dx, right? For example, if, for example, fx is equal to 0, right? The one part, we have to move that rope for 6 units. Okay. So that's equal to, now what is F1? F1 is 22. And we have to move up for 6 units, right? And plus, this one is 0, from 0 to 6, and 1.17 is just constant. Now we have to integrate this, okay? Because actually, what is it? It's force and distance, right? And together, every piece of rope, right? Because at every level, the distance traveled, let's say by each piece of rope, it is different. Anyway, so here we have 6 minus x dx, that's equal to 22.6 plus 1.17. And here we have 6x minus 1 over 2 x squared from 0 to 6. I don't need this stuff. Which is equal to 22.6. Sorry, not 22.6, 22 times 6, right? This one is times. We should not get confused. That's equal to 132 plus 1.17. And here we have 6 times 6, 36, minus 36 over 2. That's equal to 18. Which is equal to, what is 0 is equal to 0. So 132 plus 1.17 times, it is 18. That's equal to 153.06 joule of work is done to carry, actually, what is it, to lift the bucket and the rope. Okay. All right, guys, let's have some break. Okay, after 10 minutes or let's say 15 minutes, we will continue. We're running out of time. If I start now, I cannot finish this. Okay, 10-minute break.